Hi, my name is Alexander Knop and this is Introduction to Combinatorics. In the previous video we discussed how to compare sizes of different sets. In this video we are going to discuss how to find this size. The first principle is the multiplication principle. So it states that if you have two sets, x and y, then the size of their Cartesian product is equal to the product of the sizes, like this. Let us consider a small example. So let's find the size of the set 0, 1 squared. So it's easy to see that the set consists of the following pairs: 0, 0, 0, 1, 1, 0, and 1, 1. So the size should be 4. Let's use this principle to do this. So we know that 0, 1 squared has the size of 0, 1 times the size of 0, 1. And both of these sets have two elements, so the size is 4, exactly as we predicted. Let's try to generalize this theorem. So let's imagine that we have n finite sets, and we want to compute the size of their product. Apparently, we may derive that it's product of their sizes again. Let's prove this. So we are going to prove it by induction. So the base case is when we have only one set. So x1 is equal to x1. So their sizes are equal, and it's OK. So induction step. So by the induction hypothesis, we know that x1 times etc. xn has size the product of sizes of x1, etc., xn. And we need to find the size of x1 times dot 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 times xn plus 1. Note that it's the same as product of the sizes of the following sets, x1 dot 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 xn times size of the xn plus 1. And now we know that this is equal to this by the induction hypothesis. So it's equal to x1 times dot 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 times xn plus 1, which finishes the proof. Let us consider a little bit more complicated example. So let's find the size of the set of subsets of the set of numbers from 1 to n. So I claim that it's equal to 2 to the n, and it explains the notation. So the proof is the following. First of all, we need to know that size of the set of 0, 1 to n is equal to the size of the set of subsets of numbers from 1 to n. We proved it in the previous video. And after that, we may notice that size of this set can be computed using this theorem. So we know that size of 0, 1 to n is equal to the product of sizes of 0, 1 n times. And each set has two elements, so it's equal to 2 to the n. And now we know that this is equal to this, which is equal to 2 to the n, and it finishes the proof. The next principle is called the addition principle, and it states that if you have two sets x and y, then the size of their union is equal to sum of their sizes, like this. We may illustrate this theorem using the following example. So let's consider that we have two sets, 0, 1 and 2, 3. And we want to compute the size of their union. It's easy to see that the size of their union is 4 because it's just 0, 1, 2, and 3. So it's 4. But using this theorem, we can say that it's equal to the size of 0, 1 plus the size of 2, 3. And each of them have size 2, so it's 4. Like in the previous case, we may generalize this theorem and prove that if you have n sets and none of them are intersecting, then size of their union is equal to sum of their sizes. The proof of this theorem is the following. So Like in the previous case, we prove it by induction. And the base case is simple. x1 is equal to x1, so their sizes are equal as well. And induction step is also almost the same. So we know that x1 union union xn is equal to sum of the sizes. And now we need to find the size of x1 union union xn plus 1. So it's the same as x1 union xn plus xn plus 1 by the theorem, because x1 to xn is not intersecting with xn plus 1. And this one is equal to this. So this is equal to x1 plus x2 plus plus xn plus 1, which finishes the proof of the corollary. Let's illustrate this by the following example. Let's define the set 0, 1 to less or equal than n. It's the set of all strings of length at least 1 to n. And we want to find how many strings in this set. So by this corollary, we know that it's equal to the sum of these. And in the previous part, we computed sizes of these sets. They're equal to 2 plus 4 plus plus 2 to the n. And this geometric series, so we know that it's equal to 2 to the n plus 1 minus 2. So the last principle we are going to discuss is called the inclusion-exclusion principle. It generalizes the addition principle. Let's imagine that you have two sets, x and y, and you want to compute the size of the union. But you don't know if they're intersecting or not. So the inclusion-exclusion principle says that size of the union is equal to sum of the sizes, like in the previous case, but now you need to subtract once the size of their intersection. It can be explained very easily. So let's imagine you have two sets, x and y, and you compute the sum of their sizes. Note that this area, the intersection, is counted twice, so you need to subtract it once in order to get the size of the union. Let's illustrate this using the following example. So we have two sets, 0, 1 to n and 0, 2 to n, and we want to compute their union. Note that they're intersecting, and there is only one element in their intersection, which is all zeros tuple. Okay? So size of these sets are equal to 2 to the n. So size of their union is equal to sum of their sizes. So 2 to the n plus 1, because it's twice 2 to the n. And you need to subtract the size of the intersection, which is equal to 1. And so we know now the size of their union. In this video, we discussed how to find the size of the set. In the next video, we are going to discuss how to prove that the size of the set is not 0, that something exists in this set. If you have any questions, ask them in the comments. See you later.